the application of evolution to solving problems with computers. And it's really neat because you can take a problem with, you put no expert knowledge into the computer, you just tell it, you give it how to evaluate the solution, and then how to evaluate a solution and how to get the chromosome back to your actual solution. And with that, you can evolve a solution to a bunch of problems, including the 0-1 knapsack problem, traveling salesman, things that would normally be computationally intensive to solve. You can get a reasonably good approximation for it. So first, how many people know about biological evolution? So the things you need to know about biological evolution is that it's unguided, it's very gradual, it's selective over time, but it efficiently solves problems, and it's very effective at producing solutions which are well suited to their environment. So what we have to do when we apply this to computers is basically the same thing. We let loose the algorithm in an unguided fashion. Well, then we design the environment so that it'll guide all of our chromosomes and all of our solutions toward a pretty good one. The chromosomes are usually encoded just as a binary string. So it's good for some things, like solving computationally intensive problems like the 0-1 knapsack problem, the traveling salesman problem, generating the string hello world, unless you're Eric Soros. I'm just kidding. It was an easy mistake to make. But it's also not good for everything. And if you read XKCD, you'll remember this one, where the computer scientists decided to apply genetic algorithms to evolving dinner meals. And so it's not very good for things where you have a more effective solution that relies upon expert knowledge. So if you have the set of all problems here, then across the set of all problems, genetic algorithms are generally going to give a, that's a bad marker. They're going to give a pretty good solution to most of them. But then there are a lot of problems that expert knowledge can't help you a lot, but then some helps you a lot more. So genetic algorithms, other algorithms you design by hand the algorithms you design by hand won't be as versatile, but they are certainly better in some cases. So the core algorithm, what you do for genetic algorithms, is the first thing you have to do is you generate your initial population. So this is usually done by just generating random bit strings. And each bit string then corresponds to one given solution. So once you generate them, you have a function which can create whatever object you're trying to get. And so, for example, if you were trying to generate the string hello world, you would generate, you'd pick the length of your string, and you'd have a bit string of that length. So for hello world, that would be a string of length 12. So then you need a bit string of 12 times 8, because you want 8 bits for each byte. So once you have your initial population, then you start into the genetic algorithm. And what you do in the genetic algorithm is the first thing you do is you select parents. So these are just the ones that are going to be recombined to create a new set of candidates. So you select those. Then you send the parents through recombination. Then you mutate them, because mutation is very important to maintain the genetic diversity. And then you have your survival mechanism, which is just choosing between the parents and all the children who gets to go on to the next generation. And then you repeat it. And you just keep repeating it until it either until the solutions stop getting better, or until you decide that your solution is good enough. Yes?
Is this going to branch out Like as there are more offspring, you're testing more and more offspring?
No, no. That's what the survival step is for. Because if you start with an initial population of 100, you'll usually generate 100 children at this stage. So now you have 200, and at that point you do the survival mechanism. So you use one of various strategies to pick which 100 you choose to go on to the next generation. Among those, I'll get to those strategies in a little bit, but one of them that some people use is what's called elitism, where you just pick the top 100 scoring on the fitness function. So that's the core algorithm that we're going to be using. So all genetic algorithms have 5 basic components that you need to have to be able to do this. The first of them is the fitness function. The fitness function is actually the basis of all of the genetic algorithm. It's how you tell how good a solution is. So for example, for generating the string hello world, your inadequate fitness function would be, you want to know how far away it is from hello world. So what you might do is, for each character in the string, take the difference between that character and the corresponding character in hello world, just add all those differences up. So then the higher that score is, the worse the solution is. And you can either try to minimize or maximize fitness score, depending on how you set it up. If it generates something which is higher for a good solution or lower for a good solution. The next thing you have to have is you have to have your selection mechanism. And the selection mechanism is how you choose your parents. There are a variety of different selection mechanisms, which I'll get into, but that's what it's doing. It's selecting who you're going to choose to create the children. Then you have the survival strategy, which picks which of the children go on, which of the children and parents go on to the next generation when you loop through the genetic algorithm again. You have your recombination function, which is just how you take 2 parents to produce 2 children. So you can either cross over at single point, cross over at multiple points, or various other things. And then you have your mutation function, which can sometimes be tricky to write because you want a small mutation to correspond to a small change in fitness, but that's not always predictable. So, for example, if you have a chromosome that encodes a bunch of integers, if, for example, you're designing a route through the traveling salesman problem, you don't want a mutation to have you visit the same city twice. So if a mutation in that case might just correspond to swapping 2 of the elements. But a mutation in the hello world string, for example, you might just want to increment a character up or increment 1 down. And in other applications, some people just flip 1 random bit. So it varies, but your choice of mutation function has a major impact on how good your convergence rate is. So this is the environment that you're running it in. The fitness function is the equivalent of how well you fare out in the wild and how well you're doing. And it's what forces the chromosomes to go towards a better solution. So it's what makes or breaks your genetic algorithm. And it's very hard to design. If you design a bad fitness function, your genetic algorithm may never ever converge and you'll be sitting there for years. But if you design a good one that adequately scores the chromosomes, it can converge pretty quickly. And one thing that's important to note is always make sure the cost of becoming Skynet is very high, so you don't evolve Skynet. That's also from XKCD. So then, when you're designing your selection mechanism, it's the equivalent of, in biological evolution, it's the equivalent of seeing which beings in the population are fit enough to be able to reproduce. And there are many methods. One of them is called tournament selection, where you pick some K members from the population, say 5. And then from those, you pick the highest scoring one. Then you pick another 5, just picking them randomly, pick the highest scoring one from those, and those are going to be 2 parents. And you repeat that until you have enough parents. Another thing you can do is what's called roulette wheel selection, and that's equivalent to taking a spin on a roulette wheel, where on a roulette wheel, every slot has a different size. And the bigger the size is, the higher your chance is of landing in there. So what you do is you take the total fitness of all the members of the population, and then give each of them a probability proportional to its fitness in the whole population. And then you just pick a random one based off that probability. Tournament selection, in my experience, tends to converge more quickly, but I don't have data to back that up. Then you have your survival strategy, which is how you pick the next generation. And as I mentioned before, talking to Eli, you can either use elitism or you can do various other things, such as you can have generational selection, where you just always pick the children to go on to the next generation, as if the parents all died. Usually a combination of those two is effective, where you want to pick the highest scoring members of the population to go on, because then you have a better solution set. But you also want to try to keep newer solutions in more. And one problem that elitism runs into is it lowers genetic diversity. So sometimes you actually want to have bad solutions in your solution set, because if all of you, let's say you have an 8-bit chromosome. No, let's say you have a 4-bit chromosome, and you have two equally good solutions: 1, 1, 0, 0, and 0, 0, 1, 1. And these are the ideal in your population. Then you might want to generate both of those. But if you use elitism and your population you get a 1, 0, 0, and you have a few of those, it's going to overpower anything else that might involve, well, let's say 1, 1, 1. Then it could overpower other ones that will get you to this solution. So elitism can drive you, it can force you to stay in one peak that might not be the highest. So I mean, genetic algorithms are good at solving multimodal problems where you have multiple solutions. But if you select with too much elitism, then it can fall into local maxima. Then the recombination function is generally pretty simple. You just take 2 chromosomes, split them in some manner, and swap parts of them. The complexity is just where you want to swap only parts that make sense. Like if you were doing the traveling salesman problem, you don't want to swap part of an integer, so that then you would end up visiting the same city in 2. So that's where the complexity comes in. Sometimes you have to design it with regard to your problem. The mutation function, as I said before, you just want to cause a small variation in the mutation in the chromosome to correspond to a small change in the fitness function. Sometimes that's hard to do, but that's the goal. And the mutation function actually, in my experience, contributes a lot more to the convergence of the algorithm than the recombination function. So it just tends to help, because when you have a high scoring solution, a recombination with another high scoring one might not get you the right gene in there, but a mutation can get you closer. So now I'm going to switch over to the library I developed over the summer. This is a genetic algorithms library. It's generic C++, so you can actually get it off GitHub and use the API and do a genetic algorithm. As it stands with this, the only thing you have to implement is the fitness function, which is a functor if you're familiar with that design pattern. And you have to implement, that's it. You also have to implement a way to get from the chromosome back to the object, but that's really just so that you know what your solution is. It doesn't matter for the algorithm itself. So in this example, all you really do is you create your fitness, you create your objects which correspond to the fitness function, the selection algorithm, the survival algorithm, the mutation function, and the crossover mechanism. And those are all in the library if you look at it. And they're functors in C++, so that we're not using function pointers, because function pointers are hairy and evil. Then you initialize your genetic algorithm with these functors. You initialize a bunch of stuff that's important, like how big the chromosomes are, how big the population is, and you give it a random number generator, and then you initialize it, and it generates your initial population for you, that first step. And then these, the integers for the round, the population fitness and everything, those are just for your own bookkeeping, so that you know which round it's in if you want that output, and so that you can keep track of what the current fitness is. It doesn't actually affect the algorithm at all, it's just so that you can actually output that so that you can watch its progress. And then you just repeat while the fitness is less than what you want, which in my case I decided I wanted it to optimize for the ideal fitness. And you just let it go. And you just call step on the genetic algorithm each time, and it'll do all of this for you after you've passed in the appropriate objects. So it's a pretty easy library to use, if I do say so myself. So I'm going to now switch over to the I'm going to switch over to this computer, and I'm going to walk through how we implement the evolution of Hello World. After I figure out how to use projectors.
You make a good CS professor.
I know. I'm also losing my memory. So.
Did you forget your charger?
No, I think you want to try pressing the button on the keyboard.
Oh, that makes sense. So, in my make file, if you wanted to just compile everything, you run make run tests, and that'll actually run all the unit tests, which will verify that nothing's different and causing it to fail in your system. You have the right version of everything. Then you're ready to go, and you can start developing. So let's say we want to make a Hello World example. So first thing we need to do is we need to include our genetic algorithm. It's hard not being able to see it. And that'll give you the genetic algorithm. You also want to include IO string because you want to output things, because that's, nice. Then let's include vector and string because those are handy sometimes. I know that's bad practice. I'm doing it anyway.
Well, it's going to kill you.
Huh?
Using namespace STD is sometimes bad. It's not bad in this case because this is never going to be included in anything else unless you're doing something that's also bad. But since this is a one-time example, it's okay. So
It's
then,
a lazy excuse.
So then we want to implement our fitness function. So let's say, well, we know we have to have operator equals because that's what the functor uses. Okay, that beeping is irritating. I'm sorry.
Turn the volume
Down,
down.
sir.
Is there volume on this? You're right, I'm gonna make a great sales professor.
Show the volume.
Yeah, just turn sound
Hold on,
off.
make sure.
Mute it.
Okay. So, okay. So the functor is going to take in a chromosome, which is just the bit string. We want to take in a reference. Let's just call it our candidate. And then it has to be constant because you don't want to modify what's inside the functor. So the first thing you do is you say your score is 0. And then what we want to do is we want to compare this to every single element in our target string, right? So we're going to need the target string too. Does anyone know the length of a string?
It's dot size or dot length, they're the same.
Okay.
You capitalize string.
What?
The compiler will get that. Capitalized string, it's not Java. Or Java. Java.
Yeah, that's right, thanks.
Apparently C++ has garbage collection.
It's magic, isn't it?
So for each one, for each element of that, how did, okay, this implementation is going to be more troublesome than I thought, so I'm going to move on. So we're going to pretend that that works.
It's like the old magician that starts a trick and he's like, and then it's magic. Yeah.
It's done.
It reminds me of this cartoon, two mathematicians once explaining something and Nova says, and then a miracle occurs.
That's like any calculus lecture. That's why we take analysis. So then, so now I'm just going to walk through what you would need to implement inside your main after you implement your fitness function. Because that's the framework you would need for your fitness function. And you would just inside there determine your score and return it. So now I'm going to give the framework for how you would actually implement the genetic algorithm. So the first thing you would want to do is you want to get a data generator, which is a class that you've already included in the genetic algorithm. And that just gives pseudo-random numbers, and so it's handy to have. We're going to use tournament selection. So we're going to say our tournament size is, what do you want, Eric? What tournament size? 5?
Sure.
Okay. We're going to say each tournament in the tournament selection is 5. So that means we're going to select five candidates, pick one, the best one for the parents. Population size, what do you want, Eric?
20. Yeah.
Okay, let's do 20. Let's say the children's population size is the same. Because in theory, you can select a larger population size for the children than your parents' population, or a smaller one. And it's just easier if you keep it consistent. What do you want the mutation rate to be?
Should be high so it converges faster. I do know that.
No, actually,
Or low.
let's say 5% mutation rate. I think that might be too high actually, but a low because you're always going to recombine, a low mutation rate is acceptable. If you set too high of a mutation rate, you'll mutate all over the place and it won't converge. Yes.
Why are you using human reads?
Because over the summer I thought it was a good idea. I mean, you just have to be able to pass it in. The genetic algorithm itself could have the random number generator inside of it. I really don't need to have it be something passed in. I just haven't fixed that. So then we also need the recombination rate. So you want to set that something reasonably high because most of the time when you have two parents, you want them to actually recombine to create a child. But it's also sometimes good to just have it directly clone the parents because then you can keep, even if you're using elitism, you keep some of the parent population, so you maintain a little more genetic diversity. So now we want to initialize all of our objects that we're going to use for the genetic algorithm. So you need your fitness function. So So we'll call it that. What's our target? Hello world. And the nice thing about functors is that they're functions that can contain, like, they can carry data with them. So they're, if you've ever used function pointers, it's a lot like that, except instead of having to reference global variables for the data that you're trying to reach, it can just carry it with it inside of it as an object, and just uses the operator parentheses. Then you want your selection function, which we're going to use k-tournament selection, and which is just it's just tournament selection that might use more than one parent. So you're going to take an int because that's our score, and the fitness. Whatever the fitness function returns has to be something that's comparable. But as long as it's comparable, it can be anything, and that int will just be replaced with whatever it is. Yes?
So is term selection is the template?
K-tournament selection is a template. There are a few other ones in my library, including, I think I have roulette wheel selection in there also, which is also templated, which takes an integer and your fitness function. I mean, it takes whatever your fitness score type is. So in K-tournament selection, you just want to tell it what the tournament size is, what the population size is, what your random number generator is, and you have to give it the fitness function. Because that way it knows how many you want to pick for the tournament, how many you need to generate, then it has a random number generator, and you can give it the fitness. Then let's say we have generational survival, so that you just kill off all the parents after they've bred. So that's the nice thing to do. Let's just flip a random bit for the mutation. We have to initialize that with the mutation rate, obviously. And let's do single point crossover. So we'll take two parents, pick a random point in the middle, split it, swap two of the parts, and then you have your two children. So we have all the pieces we need to construct the genetic algorithm. So let's do it. I cannot spell today. So the first template parameter is your fitness function. The second one is your selection mechanism, which also is generic inside there. So you have template and a template. Then you give it your survival mechanism. Then you have to give it your mutation and your recombination. And then once you have all those template parameters, which does get verbose, you can actually give it the initial values that you want to pass in. So this is always fun with templates. If you ever used templates in C++, you know how fun getting them to compile can be sometimes. I think G++ hates giving useful error messages about templates.
G++ hates giving useful error messages.
Oh yeah, that's true. So now you have a genetic algorithm object called GA, and it's almost ready to use. You just have to initialize it so that it knows what the chromosome size is, what the population size is, and all of that stuff. So one nice thing is you don't have to say GA.set before each one, because each of the setters returns the genetic algorithm, so you can just string these together. Then you set population size. Then you set the children population size. Then you set the mutation rate. Then you set the recombination rate. I think these all have defaults if I did my job correctly. If not, file a bug report. I swear I'll get to it. but it's always good to set your own mutation rate, recombination rate, because that way you know what it is and you can tweak it to get better convergence. Because any default that I set will not be good for every application. Which is interesting, you can actually run a genetic algorithm on a genetic algorithm to evolve the fastest convergence rates. So if you want to have a fun project on your own, you do that. Then you initialize the genetic algorithm, and then you would just have your pretty little do while loop with some Boolean. And inside here, you just tell it to stop. And now you've implemented your genetic algorithm. Obviously, it's never going to terminate because you never updated finish. But after you implement the fitness function, you would also, there are getters within the genetic algorithm to get the current population, and you would use that to fetch the current population, find the highest or the average fitness, and then determine whether or not you're converging at a fast enough rate or whether or not you're close enough to a good solution. And once you're close enough to a good solution, then you would decide, okay, we're done, set finish to be true, and you would quit. So does anyone have any questions about genetic algorithms in general or how to code with this API? Yes? The documentation is the library itself. It's the nice style of documentation, you know. I'm kidding. I'm not kidding that there's no documentation, but I'm kidding about it being nice. But I'm going to switch back to my laptop, and the library is actually, like, if you look at, I have a sample folder that has a couple of samples in it. So if you model yours off of that, it would be pretty easy to follow with. I'm going to upload the skeleton that I just made after this is over, because I will put in comments saying you have to implement this here, you have to implement this here. Here's something nice to do, and then it would be ready to go. But if you go into the source and, like, if you want to see what other operators there are, what other mutation operators or what have you, you can just scroll through, and they'll be pretty easy to identify. Instead of K-point crossover, well, we used single point crossover. But then there's also K-point crossover, so anything that's recombination is probably going to say crossover in it. And then you just make sure you pick the right constructor for what you want to use. Like the default one would just set 3 split points, so it would take two parents, split them at 3 points, swap different parts of them. And then, so if you just scroll through there are some good functions.
And you can see what kind of arguments it takes.
Yeah. So that's all in the code, and if people actually want to use it, I could probably write out a tutorial at some point. I was planning on having an example ready to go that I could just like kind of cooking show, like you would do this and oh look, it's done right out of the oven. But I was busy last night visiting Brian, so I didn't get around to that. So, yes sir?
What do you do for the random numbers? Because I know when you use like the normal like srand where it sees like
yeah,
the time,
that's awful.
it's really bad. And
You
not
have,
close
I
to
think
random.
you have like 10 times as good of a chance of getting an even number as an odd number, which is not good at all. The solution that I had was I included an external library that did random number generation, and I forget what algorithm it was using, but then I wrapped that into DataGen. And the reason I created DataGen instead of using it directly was so that it would do all the initialization of that library for me, and so that if I ever decided I wanted to switch to a different one, I could just change the wrapper and none of the code would break. But if
That's
you
the
look,
way to do things.
yeah, if you look in the lib folder, I have links to where I got the random number generator from, and I have the random number generator itself. One of my coworkers, when I was entering Explorer, said it was an acceptable implementation, so I just trusted him. I ran some tests on it, and it appeared to be pretty uniform, but I don't have any data on hand, so.
I mean, it's probably better than seeding the time.
Oh, yeah, definitely. I mean, I think it does use the time in some form to seed it, but it's just a better random number generator. So does anyone else have any questions? Yes?
Say we wanted to actually use this code,
Mhm.
GPL?
I think the library is, do whatever you want with it.
Okay.
I don't really care. I'll put a license in there saying you can do whatever you want with it. I don't care.
Okay.
Because it's nothing groundbreaking. Just let me know if you use it because I think that would be cool. If you find any bugs in it, if you put an issue in the issue tracker on GitHub, I will fix it. Or if you send me an email, I will fix it.
Have you thought about making more than 2 parents?
I did think about that when I was preparing for this talk, but I think I would have to modify, the structure of the genetic algorithm to do that. Oh, no, I don't think, I would not have to modify it. Yeah, to do that, you would just write a new crossover function, and it would just do that within there. It's interesting, in the literature I've read, I guess having 3 parents converges the most quickly in the experiments that they ran. Because 4 is where you start getting lower quality parents that dilute the gene pool, but 3 gives you better combinations of the good genes than just 2. Any other questions? Okay, I think we're going to wrap up early. So, thank you for coming out. Next week.
So science has shown us that threesomes are actually the best.
No, because they do not produce, they do not have 3 contributors of genetic material to the child. Since they're actually probably statistically, they're less likely to have both parents around to raise the child, they're worse.
That's why
What about single parent households?
I don't know.
That's why we
There's
just
lots of lonely neighbors.
I'm not a biologist, I'm not a sociologist, I'm a computer scientist.
Probably the correct answer is E.
It's just lots of macaroni and cheese. Well, I did write a list of reasons why I haven't been there in Chinese.
Just a minute.
No, but it's because we write phrases out of order. It actually catches me out.
Yes, Brian normally does that.
It rains online y yo, ¡ah! Así como, pero no, me encanta.
Eso es una cosa que tienes que contar, pero cuando lo encuentras ya es...
Yo no sabía que iba a pasar. Ya, ¿qué iba a pasar? Porque...
O sea, es una
It uses Google
eso era como impresionante.
No, I'm not talking about it. Let's just say like that.
Fue un espacio infinito imprimiendo, me imprimió como una cosa así de papel.
No he empezado la peli, no voy a decir yo, oh, pero, diga
Sí, lo que pasa es que ahí no estaba yo en la computadora, sino que fue eso en el ordenador.
claro, claro, sí, sí. No,
Hace 6 años.
I was wondering, I mean, the chromosome itself is a bit.
no, por ahora no, pero ahora ese capítulo, este 4 está,
But you can have that correspond.
el test está complicado, pero eso lo dice usted.
Yeah.
Ya se sabía.